Good morning, children. Today we are going to see the property of alcohol when it acts as an electrophile. We already discussed when alcohols act as nucleophile, the bond between oxygen and hydrogen is broken. Now, alcohols can also act as electrophiles. When they act as electrophiles, the bond between carbon and oxygen is broken. And we know alcohols act as nucleophiles because there is the lone pair of electron on oxygen atom of alcohol. So it can act as a nucleophile. Now, how does it act as an electrophile? That can be observed from the mechanism where alcohols act as electrophiles. Now, look at the mechanism where the alcohols acting as electrophiles. It takes place in two steps. The first step is formation of protonated alcohol. And look at the reaction, RCH2OH plus H plus. We get a protonated alcohol. The lone pair on oxygen gets shifted to H plus and we get RCH2OH2 plus. Now the positive charge on oxygen atom makes it electron deficient. So protonated alcohol acts as electrophile. So step 2 is attack of nucleophile on protonated alcohol. This is our protonated alcohol and it acts as an electrophile, and the nucleophile taken here is Br minus. It attacks the protonated alcohol and we get a product BrCH2R, and you can see in this reaction the bond between carbon and oxygen in alcohol is broken and the nucleophile is added to carbon atom plus H2O is removed. So when alcohols act as electrophiles, the carbon-oxygen bond is broken. Now let's see few examples which involves cleavage of carbon-oxygen bond. Examples involving cleavage of carbon-oxygen bond. Now the first example is reaction with hydrogen halides. Alcohols reacts with hydrogen halide. The CO bond breaks. This is the CO bond. It breaks and OH gets substituted with halogen, Cl. So you get haloalkane as the product. Now, there is a test that you have to learn here. It is called Lucas test. This is a test to distinguish primary, secondary and tertiary alcohol. So if you are asked to distinguish between two alcohols, primary alcohol and secondary alcohol, or secondary alcohol and tertiary alcohol, we can write Lucas test. Lucas test is used to distinguish primary, secondary and tertiary alcohol. Let's see what is Lucas reagent. Lucas reagent is a mixture of concentrated HCl and zinc chloride. Now, alcohols are soluble in Lucas reagent, whereas its halides are immiscible with Lucas reagent and they form a turbidity in the reaction mixture. So, let's see how to identify primary, secondary and tertiary alcohols by adding Lucas reagent. Tertiary alcohols, when treated with Lucas reagent, gives immediate turbidity. Secondary alcohol gives turbidity in few minutes, whereas primary alcohol will not give any turbidity at room temperature when treated with Lucas reagent. So, I have written here the example, the equation with a tertiary alcohol, CH3 thrice COH plus Lucas reagent, concentrated HCl plus zinc chloride. We get the product, the CO bond breaks and the OH gets substituted with chlorine. We get the product as CH3 thrice CCl. Now, next reaction is the reaction with phosphorus halides and thionyl chloride, which you have already learned in the chapter haloalkenes and haloarenes. So, in this case also, reaction with phosphorus halides and thionyl chloride, the CO bond is broken and OH will be replaced with halogen. So, I want you to refer haloalkenes and haloarenes for these reactions. There is reaction with phosphorus halides and thionyl chloride. Now next example where the CO bond is broken is dehydration of alcohols. Dehydration of alcohols. We know that alcohols on dehydration will give alkene as the product. Dehydration means removal of water. Now the common dehydrating agents used in organic chemistry are concentrated sulfuric acid. This is a very powerful dehydrating agent. It helps to remove water immediately. Now we have a mild dehydrating agent, that is phosphoric acid, H3PO4. So we have two dehydrating agents commonly used. One is a strong dehydrating agent, concentrated sulfuric acid, and the other is a mild dehydrating agent, phosphoric acid, H3PO4. Now I have written examples here, 3 examples, and the examples are with a primary, secondary and tertiary alcohols. The first example is with a primary alcohol, C2H5OH plus concentrated sulfuric acid at 443 Kelvin. H2O is removed and we get alkene as the product, ethene. Second example is with a secondary alcohol. Now instead of sulfuric acid, I have used here phosphoric acid, that is 85% phosphoric acid heated at 440 Kelvin. You can see this is an example for beta elimination reaction. Beta elimination reaction means a 1,2 elimination reaction. That is, this is our alpha carbon and this is beta carbon. This is also our beta carbon. Alpha carbon, beta and beta carbon. Now OH is removed from alpha carbon and hydrogen can be removed from either of the beta carbon atoms. So I have removed hydrogen from this carbon. I get the product as CH2 double bond CH3 plus H2O is removed. Now the third example is with a tertiary alcohol. Now you can see the oxidizing agent used is 20% phosphoric acid. And lower temperature is needed for this reaction. Now here also, as you can see, beta elimination takes place. This is our alpha carbon and all the 3 are beta carbon atoms. Hydrogen can be removed from any of the 3 beta carbon and OH can be removed from here. Now I have removed hydrogen from this carbon, so you get the product alkene plus H2O. Now the question, why for primary alcohol a strong dehydrating agent like concentrated sulfuric acid is used, whereas for secondary and tertiary alcohol mild dehydrating agent is used? Now the reason is, when we study the mechanism, after this we are going to discuss the mechanism for acid catalyzed dehydration of alcohol to form alkene. In the mechanism you can see it involves the formation of an intermediate carbocation. And we know tertiary carbocation is highly stable. So tertiary carbocation, since it is highly stable, it gets dehydrated very quickly, even with the help of a mild dehydrating agent like phosphoric acid, followed by secondary alcohol, followed by primary alcohol. So you can say the order, the decreasing order of ease of dehydration of alcohols is tertiary greater than secondary greater than primary, which means tertiary alcohols will be dehydrated easily, followed by secondary, followed by primary. So tertiary alcohols and secondary alcohols needs only mild dehydrating agents like phosphoric acid for dehydration, whereas primary alcohols needs very strong dehydrating agent like concentrated sulfuric acid. Now next we are going to discuss the mechanism for acid catalyzed dehydration of ethanol. And we know ethanol on dehydration we get ethene as the product. So it takes place in 3 steps. The first step, step 1, is the formation of a protonated alcohol. So we are starting from ethanol. This is our ethanol. In presence of acid, H plus, we Here this is the primary alcohol. So we take concentrated sulfuric acid. H plus comes from concentrated sulfuric acid. You know, it helps in the formation of a protonated alcohol. The lone pair on oxygen gets shifted to hydrogen. And this is a reversible reaction and it's a very fast reaction. The protonated alcohol formed is this. Now, second step is the formation of intermediate carbocation. So, in the second step, the protonated alcohol will slowly form an intermediate carbocation. You can see how this is formed. The CO bond is broken, that bond pair is shifted to oxygen and this part is removed as H2O. And you get a carbon carrying positive charge, that is a carbocation. Now the third step is deprotonation or removal of H plus from carbocation to form alkene. So in the third step we can see one of the hydrogen atom will be shifted to this position and we get alkene as the product by removal of H plus. So this is the mechanism for acid catalyzed dehydration of alcohol to alkene. Takes place in 3 steps. First step is the formation of protonated alcohol. Second step is the formation of carbocation. Third step is deprotonation to form the final product alkene. Thank you.